Let us learn about the sixth property, that is property number 6 in this particular class. So property number 6 of the skew symmetric matrix, you must have a look. Okay, if A is a skew symmetric matrix, if suppose A is a skew symmetric matrix, then what will happen? Ka is also skew symmetric matrix. Okay, what does it mean? Let us see what does it mean. If A is a skew symmetric matrix, then Ka is also a skew symmetric matrix for any scalar k. For any scalar k, if A is a skew symmetric, then Ka is also skew symmetric. Okay, if A is a skew symmetric matrix, then Ka is also a skew symmetric matrix for any scalar k. This thing you must remember. Scalar means constant k. Okay, if A is skew symmetric, then k times of A, that is where k is a constant. K times of A is also skew symmetric matrix where k is any constant or any scalar. So how to prove this? Let us prove this. In order to prove this, let us have the following. A is skew symmetric matrix. Now A is skew symmetric, so it means that A transpose will be equal to minus A. Obviously, A is skew symmetric matrix, so A transpose will be equal to minus A. A is skew symmetric, so A transpose will be equal to minus A. Let us assume this is equation number 1. Let us assume this is equation number 1 where A transpose is equal to minus A. This is by definition of skew symmetric matrices. This is by definition. This is by definition of skew symmetric matrices that A transpose would be equal to minus A. This term is from the definition of skew symmetric matrices. Okay, let us assume that this is equation number 1. Let us assume that this is equation number 1. Okay, now k times of A complete transpose, k times of A complete transpose is equal to k times of A transpose. This is from the property which we had learned in the previous lectures. This is from property which we had learned in the previous lectures, that k times of A complete transpose, k times of A complete transpose is equal to k times of A transpose. Okay, k times of A complete transpose is equal to k times of A transpose. This is the property which we had learned in the previous lectures. Okay, so complete k into A. If we take k into A and take its transpose afterwards, if you multiply A by k and take its transpose, if we multiply A by k and take its transpose, then it is equal to multiplying it by A transpose, multiplying the constant by A transpose. It is equal to multiplying the constant by A transpose. Okay, so this is the thing. K times of A complete transpose is equal to k times of A transpose. Now A transpose is equal to minus A by definition of skew symmetric matrices. Okay, by definition of skew symmetric matrices, A transpose is equal to minus A. Okay, so this A transpose can be replaced by minus A over here, and this minus sign can be written in the front. This minus sign can be written in the front, and it has been written in the front. The minus sign has been written in the front. It has been written in the front. Okay, so k times of A complete transpose is equal to minus Ka. K times of A, Ka complete transpose, Ka complete transpose is equal to minus K. Ka complete transpose is equal to minus K. So Ka is also skew symmetric matrix. Clearly Ka is also skew symmetric, because by definition this particular thing is satisfying the definition. This particular thing is equal to this is satisfying the definition. It is satisfying the definition. So Ka is also skew symmetric matrix. So Ka is obviously also skew symmetric matrix. Okay, so this is the thing. So the property says that if A is a skew symmetric matrix, then Ka is also skew symmetric matrix where k is constant or k is a scalar. If A is a skew symmetric matrix, then Ka is also a skew symmetric matrix if k is any constant or any scalar. Okay, so this is the thing. If A is a skew symmetric, Ka is also skew symmetric if k is any scalar or any constant. Thank you very much.